about here. So let me share my screen. This is what I was talking about in terms of where we are. We are picking up from where we stopped last time. We solved this problem, all right? You can see now the question which, we are asked to, or we are required to calculate the heat of neutralization or reaction, heat of reaction, which if you are given the mass, all right, mass and change in temperature. Sometimes you can be given the change in temperature. Sometimes you may not be given the mass, but you have to determine the mass by, factoring in the solute and the solvent for neutralization. This equation here, I'll give you in the exam. This is the equation I gave you, that if you have 3, you can calculate the fourth one, change in temperature. Let's see, I didn't solve this problem on last time, the neutralization here. I would like to pick up from here that if you are given a problem such as the one you see on the PowerPoint slides, when 6.50 grams of a solid sodium hydroxide dissolved in 100.0 grams of H2 in a coffee cup calorimeter, the temperature rises from 21.6 to 37.8. Calculate the quantity of heat in kilojoules, all right, in kilojoules released in the reaction, This calls for using this equation, but you need to synthesize and look at what you are given. Are you going to use these 100 grams? Are you going to use 6.50 grams, or it will be combined? Remember, this equation on the whiteboard stands for mass of the solution in this case, which means we are combining the solute and what? And the solvent to get the mass of the solution. So for this problem, you will use this heat of reaction in joules, all right, is given by the mass, in this case, solution times specific heat, all right, times what? Times change in temperature, We can find this, all right? We can find the change in temperature by, dividing it by, or subtracting from the equation. This is from the difference, T final minus T initial. T final minus T initial. Can you see, everybody, can you see my screen?
Yeah.
All right, thank you. All right, just want to make sure that we are all on the same page. So T change in temperature is T final minus T initial. This F for final and I for initial, which we have to find by finding the difference. 7.8 minus 21.6, and the difference here is change in temperature here is 16.2 degrees Celsius. The specific heat, you will be given this, and for this problem, the specific heat in joules is 4.18 joules per gram times degrees Celsius. This is the specific heat of what? Specific heat of H2O. A specific heat of H2O with this solution. And now mass, for this is 6.50 plus 100.00. So the mass we'll use is 106.50 grams. So that when we plug in the equation, unit reconciliation, the unit reconciliation here is now 106.5 grams times, this is the mass, times the specific heat 4.18 joules per gram times degree Celsius times 16.2 degrees or Celsius, so that degrees and degrees will cancel. The grams and grams will cancel. We are left with the units in. If we multiply that, let me just get my calculator. If you plug in your calculator, looking for my calculator here, if you multiply the units given, all right, units given, this is around 7.721 to 3 significant. This is kilojoules. What I've changed here is changed to kilojoules based on the what? Based on the question here that it got to be in kilojoules. Elsewhere, you are given this, or you are expected to know this. Remember the prefixes? Yes, we will be using throughout the prefixes. Kilojoules, 1 kilojoule equals to 1,000 joules. Let me come back to the question here, that where do we get 4.18? It is the specific heat of H2O. You will be given that, but since if it is homework assignment, you'll have to look for that. I'm trying to look for that slide right here. The specific heat of H2O or water, liquid H2O, is 4.18. I don't expect you to memorize the specific heats for the few substances given on table 5.1, but you will be given for the problem, okay? So in this one, this was a specific heat for H2O. It will dissolve, that's what you will be given. Sometimes you may be asked to determine the what? The specific heat and identify the substance. So don't worry about that, you will be given. But if not given, you are expected to use your text to determine and figure it out that what am I dealing with here. So you'll be given that for a specific problem. Thank you. I've let them in, Tanya. I've let them in, so they should be in now. So that is,
Professor?
Yes.
Sorry, I just want to make sure. So whenever we do these problems, would we ever be given like 2 specific heats, like one for the sodium hydroxide and one for the water, and have to choose, or will we always be doing the specific heat in the equation for the solvent?
For the solvent,
Okay.
Even for, aside to that specific, when we get to neutralization, you will use H2O. If you have an HCl and you have sodium hydroxide, to give you an example, you have 2 reagents, right? And you're wondering what it is, because it will neutralize. At the end, you'll have H2O. So you'll be given for 1 H2O.
Got you. Thank you.
So that is where the 4.1 came from. And sometimes the specific heats are given in calories per, you have to look at the units given, that this can change to calories. It doesn't really matter, you'll be given the calories per gram times degrees Celsius. That means you'll end up with the unit in calories, but for joules is what we will have to go by. is how what we have to go by. Now, this is in kilojoules. If you look at the requirement here, this got to be in kilojoules, and say released. I know last time we talked about when we say release, that means it's exothermic, and we put a negative there to show that it is released. I know when we say positive, I was looking at this. This is on page. You want to practice with it, page 206. This problem is page 206, number 55 in the lab manual. You don't have part A, but that is the answer for part A. This is the answer for part A. Now let's look at part P. Using the results in part A, which you already know the amount of it released, calculate the envelope of reaction in kilojoules per mole of sodium hydroxide. If it was per mole of, H2O, and then you'll have to find the number of moles. So this B, it is the heat of reaction in kilojoules per mole of what? Mole of NaOH, which means you'll have to change these grams to moles using the what? Using the molar mass of H2O, number of moles, not H2O, but sodium hydroxide, number of moles of NaOH is given by, all right, 6.50. This is grams of NaOH. I'm just using the molar mass times 1 mole of NaOH weighs around 40. Let's just use approximate, use the periodic table. It's around 40.0 grams. If not given this, you will have to use the periodic table. All right, I'm gonna go back to A. Let me just finish this. Somebody has a question. This will give you the number of moles. This is the number of moles of what? 1.625 moles of what? Moles of NaOH. Since we know the number of moles of NaOH, all we have to do is divide negative 7.21 kilojoules over 0.162 This is moles of NaOH. This is around 44.4 kilojoules per mole of what? Per mole of NaOH, per mole of NaOH. That's how to find the number of, the energy given off per mole of, assuming that the specific is the same as for pure water, which is the same as what we have it here. Now, any question on B? Someone has a question, Selena? You're wondering if we could go back to our first part A calculation. All right, right here in part A, this is problem number 55.
Oh, was there one before that where you got, I was wondering how you got 106.5. That's all I was wondering.
Yes, it is the mass of the solution. If you look at this equation, it got to be the mass of solution. You see this right here?
Yes.
So it is understood that how do we end up with the solution? Solution is obtained when you mix two things, which is the solute, the less component plus the solvent. This is 100.0 and this is 6.50. That is where the 106 came from, because to end up with the solution.
Oh, okay. I understand now. Thank you.
Yes. Yeah, the challenge with this is as we go along, right? more concept we learned earlier on, you are expected to recall that it is not one-stop shop that you will find everything in the problem. They expect you to be proficient in knowing or figuring out stuff. For example, here, kilojoules. If someone doesn't know how to change joules to kilojoules, and they assume that you are still on the same page, same chapter, you can flip over the textbook and look at the specific heat of H2O. So that is how you find the energy given off per mole. And if you look also this problem B, it is a compound problem in the sense that no one will tell you that how do I change from grams of sodium hydroxide to moles of sodium hydroxide. It is by using the molar mass as a conversion factor. There's another problem you are expected to know. And then in chapter 2, we learn how to write the correct chemical formulas for compounds. So if someone doesn't know the chemical formula for sodium hydroxide, use the wrong chemical symbol for sodium, use the, wrong formula for hydroxide, you don't know anything about the polyatomic ions, it will be a challenge. So there are multiple problems in here, translating the chemical names to formulas using the periodic table, but sometimes you may be given the molar mass to save time. So that is what you need to remember for determination of heat of reaction. More so in calorimetry, you will solve problems on heat of neutralization. Hopefully this information will help you in the lab. I think it's lab number 10 on the calorimetry. Please practice more on the heat of neutralization using calorimetry. I will not ask you any problem on the pump calorimeter, which measures the total internal energy of a system. Now, in some reaction, all right, some reaction is impossible to determine its envelope of reaction or heat of reaction. What do I mean by that? Maybe there are about 10 equations before you end up with the final equation to for a particular reaction. What I mean by that is we can have equation 1, which will form some product. Let's say product what? Product 1. In equation 2, we have product 1 being used to form product 2. To here, and then equation 3 here, we have product number 3 going to final product in this case. These multiple steps, all right, it is sometimes used to find the overall. We have right here overall, let me just give you that, overall reaction or equation. Hess, who was, Hess, his name, is a scientist who came up with a law which states that the heat of net reaction, or if we have an overall reaction here, is the sum of individual heat of neutralization. So if we know the heat of neutralization for equation 1, for equation 2, for equation 3, we can determine the overall net reaction. So in other words, change in enthalpy for the net, that is overall, is given by the summation of individual heat of reaction for individual equation. It is the sum change in enthalpy of reaction. This stands for sum change in enthalpy enthalpy of reaction for individual equation. So how do we use this? So if we have change in enthalpy for many reaction, we can find the sum, that is the overall. We can calculate the overall enthalpy using the individual published values for each of the individual equation involved in all the equation. So the Hess's law series, if you look at this series, this is the same as equation 1, equation 2, equation 3. In other words, to arrive at the final product, their overall or their individual reaction. That overall reaction equal to the sum of enthalpy changes for individual step. So in other words, this may be, let me just change enthalpy reaction 1, enthalpy reaction 2, enthalpy reaction 3 here, so that enthalpy for reaction will be given by delta H1 plus delta H2 plus delta H3. You will be given thermochemical equation for equation 1, for equation 2, for equation 3. And for the overall here, it will be the sum of all these enthalpy. Sum of all enthalpy. This is what we call Hess's law. This is what we call Hess's law. And before we look at the Hess's law, recall the properties of enthalpy of reaction. Recall the properties. What do I mean by properties? It is extensive, which means it depends on the amount of, the reagents. That means the more we have, the amount of a reactant, the larger the enthalpy for reaction. So if we multiply the equation by a factor, we'll also multiply the enthalpy for that reaction by a factor. If we reverse the equation, that means the sign of enthalpy for reaction will do what? Will change. If we divide the equation by 2 or by a factor, we will have to divide the enthalpy for that step by that factor. Those are the properties we looked at last time, which are handy in Hess's law. We're just going to use those properties. It's Hess's law. And the summation you see here, all right, I know we looked at this. I don't want to go in details on how we end up with that, probably for looking at individual equation for this Hess's law. If you look at equation 1, equation 2, equation 3, this is a thermochemical equation because we have what? The heat component. This shows it is exothermic, endothermic. Positive, negative, negative. Remember exothermic, endothermic? Now, if I multiply any of these by a factor, I'll multiply these guys by any factor. If I divide by a factor, I'll have to divide this by a factor. We don't do crazy stuff like raising it to something else. No, we don't do that. Now, in Hess's law, you will be given a series of individual equations, and then the overall one, the highlighted one on the PowerPoint slide, is what the question is asking. Calculate the enthalpy for what? This overall equation based on this individual. How will you do that? It is by doing the inspection, by looking at the product, by looking at the reagent in the overall, and reconciling with each individual thermochemical equation to figure out how do we end up with this. For example, all right, in the overall equation here, ethylene. You may not know the name of this. Ethylene, C2 double bond, all right? It is coming from the last or the third equation here, the third thermochemical equation, but the equation has been reversed. So that means to end up with this equation right here, we will have to reverse equation 3 so that the products become the reagent. The reagents become the product, and then the sign on Endelave reaction will change. If I look at equation or if I look at the coefficient for hydrogen fluoride, HF, it looks like I have it on the product side and I have it on the product side in equation 1, but I do not have to change that because if I flip, it will mess up the overall equation too. So what we need to do is what? Multiply this. It seems like we multiply the first equation by 2. So if I multiply by 2, I'll end up with 4 moles of hydrogen fluoride. And this means it's not only that individual. By the way, when you multiply, it is not only that individual species in the equation, it is the entire equation. So that means we'll need to multiply by 2 equation 1. So what I'm saying here is, since equation 1 is multiplied by 2, we'll end up with the 2 moles of hydrogen gas plus 2 moles of hydrogen, fluorine gas to produce 4 moles of what? 4 moles of hydrogen fluoride gas. And when we multiply by 2 that, Endelave for reaction for this is multiply by 2, all right? And the equation, we multiply that by 2, we'll end up with 10. This is negative 10, 74 kilojoules, 1074 kilojoules. I'm multiplying this equation by 2. How do I know it is by 2? Based on the species in the overall equation. If I look at equation 2, carbon tetrafluoride, CF4, we have multiplied by 2. We don't need to change the equation 2, the chemical equation 2 here. That means we'll have to multiply by 2 to end up with the 2 carbon in this solid plus 4. It's gonna be 4 now because I'm multiplying by 2 moles to produce 2 moles of carbon tetrafluoride. This is gas. And delta H for this equation is modeling by 2 is negative 1360. 1360. How do I know I need to multiply by 2? It's based on what I have in the final equation, that this species has been multiplied by 2. And I need to do the same thing for the entire equation, including the Endelave for reaction for this. Now, if you look at now, this is what you need to pay attention, that the last equation has been flipped. That means it has, you flip the equation that the product became reagents. What I mean here is C2H4, this is gas, produce 2, see, this is solid, plus what? Hydrogens, 2 hydrogens right here. And the Endelave for reaction for this is negative what? Negative 52 0.4. When you reverse the equation, the sign for Endelave changes. when you reverse, the enthalpy for reaction changes. So in other words, the overall, you need to pay attention to how you end up with this. This is the overall. Just like the net ionic equation, you cancel out what is a spectator or what look like. What look like? We don't call a spectator in this case. If I bring down everything and cancel what look exactly the same, if you look at the carbon solid, it will go away with the carbon solid on the what? On the reactant side and product side. If I look at the hydrogen stars here, it will go away with that and it will go away with that. And the overall equation will be C2H4 gas. Now, 2 plus, they look at exactly the same thing, 2 plus 4, if you look there on the reactant side, that is where the 6 is coming from. It's not coming from balancing the equation. It is just coming from the summation. Remember the basis or the definition of SS law is just a summation. So we are summing, not balancing. The 6 F2 is from the summation of this and that. To produce, I don't see anything else here. It is just 2 CF4 gas plus 4H4. So we do not, you are not given the overall equation. In SS law, you are not given the overall equation, but you will derive from the individual thermochemical equation. Now, the question is, the enthalpy for reaction for this reaction is given by delta H1 plus delta H2 plus delta H3. 1, 2, and 3, 1, 2, and 3, right? Is coming from this 1, 2, 3, which means you got to add the way it is. You don't need to do anything. The trick lies behind manipulating the equation such that you end up with the 3 equations. When you cancel out what look exactly the same way, you end up with the overall, and then you add what you have for the enthalpy for reaction for individual. In this gives you -2 4 to 8, all right, point to what? Anybody got the same answer when you add the two, all of them? The summation. Is it 284? I need to find out. Something is wrong. Somebody check.
Yeah, I got -2,486 points.
2,486, right?
Yes.
2,486. 2,486 point what?
0.4.
0.4 kilojoules. Kilojoules, 2,400. So here, what I miss here is dividing it by 2. Sometimes if I had, let's say for example, I had only HF in the final equation here, that means I need to divide this equation by 2. I'm just making up that. That means I'll have to divide this by what? By 2. So the key thing is looking at this. For most problems, you may have only 2 equations. 2 equations, it is very easy to look at what? It is very easy to look at how things have been manipulated. But the more thermochemical equation you have here, you can imagine if you have 10. If you have 10, I'm not saying I'm gonna give you 10, but at most you may have 4, you may have 2, most, but the sole has to do with manipulating the equation. This Hess's law is used in a situation where determination of enthalpy for reaction cannot be determined just by a single equation, but a series of equations. Any question on Hess's law?
Did you say we'll always get the final equation or we won't have the final equation?
You will be given, of course, you will be given the final equation. You'll be asked, calculate the enthalpy, because if I ask just only to calculate the enthalpy for what? It can be any reaction. So you'll be given this in order to figure it out what happened in all these three equations. If it
Okay.
just been multiplied, if it just been divided by, if it just been flipped. So
Okay.
yeah. Any other question? All right, sometimes if you are given the overall for this, in other words, if you are given this right here, if this is for the overall, if this is for the overall, all right, and you are not given for this, you are not given, and you are given on that and given that, you also have to do the math and say, if I have for overall, I have for this, I have for this, and I'm not given for the second one, you plug it and assume it is X. Take it from there. Enough of the Hess's law. Hess's law is basically used to determine the enthalpy for reaction for overall. Now, enthalpy of formation with the subscript F, you'll see this notation for formation. Subscript RXN is for reaction. Somebody ask a question? Wait, is he actually gonna win this? Wait, did they actually not end? Wow. Gotta mute everybody. Somebody was unmuted. All right. You didn't have a question. So enthalpy formation here, delta HF stands for enthalpy for formation and is defined by the change in reaction in which a compound is made from the constituent elements. I have highlighted the compound and the element. This is a compound, all right? Made from the constituent elements, oxygen and hydrogen. The connection between atoms in this, of course, we looked at this in intro to chem, how the compound is written structural compound. This compound, if you look at the structure from the elements, we can calculate the standard enthalpy of formation. You will be given that this subscript standard enthalpy of formation. Always the subscript stand for standard. When we say standard, at standard state, maybe recall what you, it's going to come back again. Standard temperature pressure, temperature in Kelvin 298.15 K, molarity 1.00 molar, and of course the pressure is 1 atmospheres. So we can calculate the standard enthalpy of formation of a compound or for reaction from these standard enthalpy of formation for what? For few selected compounds. Table 5.3 shows the enthalpy of formation of each compound in kilojoules per mole. in kilojoules per mole. Where we are going to with this is using this equation, enthalpy of formation or change in enthalpy for reaction at standard state. It's gonna change now to what? It is not delta H alone. What this means is a standard superscript 0 is given by the summation of, let me use M here, or N, enthalpy of formation of products minus, or rather minus the summation of M, and by the this is superscript node, standard enthalpy of formation of reactants, where N and M are coefficient in what? Coefficient in balanced what? Balanced equation. This equation here, if you know, of course, everybody knows how to interpret the chemical equation, product reagent separated by the R. Product minus reagent. In this case, you'll have to refer to table 5.3 with this homework. If you are not given in the problem, you have to refer to this table and plug it in this equation. Where are your reagents? Solving one problem here will help. If I look at this equation here, I should be able to identify the products. I should be able to identify the what? The reagent, and we multiply by 3. If I look at the product minus plus, so I'm gonna add this N stand for the coefficient for CO2 times 3, for H2O times what? Times 4. So if this was homework assignment, I look for CO2 and liquid. Please be careful with the physical state. If I look at the CO2, there is liquid, or I mean, there is solid CO2 and there is gaseous CO2. So for gaseous CO2, we have the enthalpy of formation for that. For liquid H2O, this is the enthalpy for formation. So if you don't pay attention, somebody might use the enthalpy of formation of gaseous H2O. It will mess up your calculation. So where we are going with this, you'll be given that, so that when you are presented with this equation, liquid H2O, gaseous CO2, and then you subtract times 5 for what? For oxygen gas, and then times 1 for propane. This is propane gas. So if I know propane, CH2CH3, you'll have to plug it in the equation. You'll be given that. You'll be given for propane, CH3H8. These are just few examples on how we use that. So if you look at this, I'm just going to, I don't want to go in step by step. If you look at this equation at the last right here, this is what is happening. M for the coefficient in the balanced equation for the reactants. N is the coefficient of what? The balanced equation, the coefficient for the product minus reagent. We can calculate this from the standard enthalpy of formation that for propane, we multiply by 3. That is where the coefficient comes in. This is for the CO2. Where is this value? I don't expect you to memorize. You'll be given, but of course, if it is homework assignment, MindLab and mastering, you'll have to refer to the table. But in the exam, will be given in the problem that the envelope formation for this CO2 liquid H2O, you multiply by 4 kilojoules minus now the product minus reagent. This is the envelope formation of propane cars. And the standard envelope formation of an element is given. You'll be also given as 0. If you're not given for an element, it's 0. If you're not given in the problem, take it that as 0. So this standard envelope formation for product reagent you will be given. It's just to illustrate what is going on. The most important is how do you use this equation? Where are all these values coming from? You'll be presented and you are asked to find the standard envelope formation for our product. It's just continuation of our Hess's law, product minus reagent. Any question on using the standard envelope formation to calculate the standard envelope for reaction?
I just had 2 quick questions. So
Yeah.
one of them, whenever it is the separate steps that you were showing us before, would we need to like derive all of those separate steps, or is that just going to be provided to us like the 3 different equations, like in that last learning check?
Oh yeah, you'll be given only the overall equation and you'll be given these values that are standard. So let's say, for example, this one, right? You don't need to use Hess's law to derive each one of them, so long as you know you have been given the standard envelope formation. And how will you know that this is different from the Hess's law? Hess's law, you will be given 3 equations and nowhere is given the standard, but for this particular, you will be given an overall equation and the standard envelope formation for each species in the reaction will be given, and then you know that is what I need to plug it in this equation on the whiteboard. And if you look at the subscript right here, it means standard envelope formation, which means you'll be given formation for this, formation for that, formation for that, formation for that. In Hess's law, you will not see this, you will not see this, and you will not see that. And you will not be given the standard formation for each species.
Okay, got you. All right, and then what were you saying about the 0 kilojoules? I missed that.
Oh yeah, for an element such as oxygen gas, you'll be given that. If you look at the table, let me just, I don't know if they have it right here. For oxygen gas, it is 0. Some of them you may not be given, it's assumed to be 0, but for elements, they are always, because if you think of oxygen, it is already there. Oxygen is used to make something else. But let's say for ethylene, it is made from carbon and hydrogen. So we have the envelope formation for that. But if something is just an element, it is already, we don't account for atoms which make up that element.
Okay, I see.
Yeah.
All right, thank you.
So it's given for that. But what I've seen, all right, what I've seen in terms of the 0, you may be given as 0. Sometimes if you are not given, assume that it's for an element. Elemental said always the envelope is taken as 0. And all you have to pay attention is the balanced equation. All you have to do is the balanced equation. In a similar way, we can use the Pond envelope. Pond means, you know, chemical bond. A bond is strong electrostatic force between 2 elements. If a bond is broken, energy is given off. You know, bond formation, bond breakage, energy is needed to break that bond. The energy associated with the bond formation or breakage is called envelope, bond envelope. And we can also use this to calculate the envelope for reaction. This from the bond cleavage or breakage between chlorine atoms from individual all right, chlorine molecule to form individual chlorine atoms or methane, CH4, carbon 4 hydrogen. We break this bond, we break this bond, we break this. We call this bond envelope, the energy required to break a bond. I know you may have covered previously that the strongest bond, double bond, single bond, and triple bond is stronger than double bond. Double bond, single bond, I can easily break that. Double bond is hard to break. If I have triple, and then it's even harder to break. We will see how to use the bond envelope to calculate the envelope of reaction. In simple terms, you will be given the energy associated with each bond formation. Energy is released when a bond is formed. Energy is required to do what? To break that bond. There is a table which I want to share with you. You will be given that and show you how you can use that in calculation of envelope of bond formation, similar to what we have for the product. If you look at this, it involves different elements and understand double bond or three lines stand for triple bond, single lines mean single bond. What this shows is how much energy is given off or how much energy is required to break this bond. And it's the same thing, energy to form this is given off. So that if you look at the single bond and double bond, it's the same as what? It's the same elements right here, but the amount of energy required to break double bond is greater than the amount of energy to break a single bond. If you look at these same elements, carbon and oxygen, to break or to form this is the amount of energy required to break this. This is the amount of energy required to break this. And in a similar way, if you look at this, I don't want to get in details, the trend on how this one is happening, go down the periodic table. But ours is to find out how do we use this bond envelope in calculation for the reaction, You need, how we use this, if you look at the envelope of reaction, change in reaction, it is the summation of how many bonds are broken and how many bonds are formed. Summation of bonds envelope is broken. Bond envelope is formed. And then we add all of them, made, subtract the bonds for all broken. So if you think about this, bonds made, that means it is the product. So product, because we are breaking the bonds in what? In the reagent, you need to break that. So let's see how this equation works. If we have, if you look at now the reaction of, in this case, the bond formation, you need to see how many bonds are broken, how many bonds are broken, how many bonds are formed. At the outset, either you will be given something or individual for each bond involved in a chemical reaction, not necessarily this table, but if chlorine, fluorine is involved in the reaction or oxygen is given in the reaction, you'll have to use the Pond and the Lapis of formation form to plug it in this equation so that we can predict the chemical reaction. If it is formed, at the outset, you have to have this table for, in the homework assignment, I'll recommend that you look at this table. You should be able to write the structural formula for compounds involved in a chemical reaction. For example, here, how are we going to use the bond and the Lapis? The question will be, use the bond and the Lapis in table 5.4 to estimate the enthalpy for reaction for combustion of ethanol. Combustion, that means oxygen is involved, oxygen gas is involved. I always, since we haven't looked at the structural formula, this will come in chapter 8, I'll try to give you structural formula so that it will be easier for you. It will be easier for you to figure it out how to write or calculate the enthalpy for formation for the product. What do I mean by that? If I look at this equation, ethanol, if you look at ethanol, combustion of ethanol, how do I know even the chemical formula? Ethanol C2H5. We haven't looked at this before, like how to translate this plus. This is, they expect you to write the chemical formula, combustion of alcohol. This is an alcohol, produces CO2, all right, CO2 plus H2O. We haven't looked at the, writing the structural formula. Let's see, balanced equation. This is one thing we learned before. Balancing the equation, this was chapter 3. And one right there. Balancing the equation, we learned that they expect you always balance the equation before you do anything else. But the challenge is, how do I know the structural, how do I relate to this bond and the Lapis concept? This is what I, you'll see in the quiz, probably exam, is translating now the molecular formulas to structural. This is the structural formula for ethanol. Always carbon form 4 bonds, some of you already know this, plus oxygen will always be double bond, and there is a 3 in front of that, going to, this is the structural formula for CO2 with a 2 in front of that, plus 3 H and then O H on that side, hydrogen. If you look at the product here, you are wondering, how do I'm translating this so that I use the bond and the Lapis. That in the product and the reagent, for example, in the first reactant here, ethanol, we have to break CH, we have to break CH bond, and you count how many you have. We have 1, there's 1 here, 2, 3, 4, 5. So we have 5 of those, which means we'll have to multiply by 5. We have to multiply by 5. The only way you can proceed with these bond and the Lapis problems is to have the structural formula similar to that. And I promise, just to make life easier for you, problems will have structural formula so that you see how many, yours is to count how many you are breaking. So I started up with CH, carbon, hydrogen. And how many do I have in this molecule? I have 1, 2, 3, 4, 5. And then I can say there is carbon, carbon. And in carbon, carbon, we have only one on what? We have only one on the product side. So 1 times 1 equals to that. So you look at that. Then the what? There is carbon, oxygen. So 1 carbon, oxygen, 1 carbon, oxygen, 1 times, and then 5 times. And then there is 1 oxygen, hydrogen. So we have to multiply 1 time. See how many bonds we are breaking. How many bonds we are breaking. Out of this, we can determine the bond envelope required for that. And then for oxygen, oxygen, there is a double bond. How will we end up with this? I expect you to know that, you know, the oxygen molecule has a double bond because each one of them has 2 unpaired, so there's gonna pair them. So we will have also the what? The oxygen 3 times oxygen double bond. This will be 1 times what? No, 3 times. We now go to, this is what they were talking about using this table right here. Carbon, this is 413, 413. For carbon, carbon, right here, 348. Carbon, oxygen, 358. Hydrogen, oxygen, 463. And then oxygen, oxygen is 495, 495. The question was, use table 5.3. In the problems, you'll be given the, you know, for each bond being broken. You will do the same thing for, you know, this is a reagent. We account for that. And then for product, there is carbon, oxygen, and there are 2 of them. And then we multiply by 3. How do I know that? It's based on what I do have here. If you look at, there's 3 here, this was 3, I meant to say 3. There is 1 here, and then there is another one here. So I have 2 oxygen, carbon, and then from the balanced equation, it is 3. So I multiply by 3, that is where the 3 is coming from. I have 2 carbon, oxygen bond, broken. And so basically here is 6 times 2 of it, all right? It's the same as the energy broken for that. Hydrogen, oxygen, we have 2. And if we have 2 times 3, is it 3? This was 2. Yeah, this was 2. I meant to say 2 times 2. So this is 2, not 3. And then this 3. So this is 4. We'll multiply by 4 carbon, oxygen. 4 times 799 kilojoules plus for the reagent 3 times or 6 times oxygen, hydrogen is 463. So if we have for product and reagent, we'll now look at this equation. Summation of bonds and the lapis of Procan. We are breaking. Be careful with these two equations. There is the standard envelope, the one we had a subscript, it was Procan. I mean, it was product minus reactant. Remember, standard was product minus, but here is bonds being broken. That means the Procan is on the reactant side. We are forming bond envelope is forward. The product. So if I know the summation for product is the summation, so I'm just gonna add all these forward for the product, put it right here. For the reagent, which I do have here, I'm just gonna put it here to calculate the bond envelope is using the equation or using the bond envelope is for reaction. This is an example on how I walk you through how to draw the structure. You may ask, how do I know in the exam how the structure look like? I'll strive, listen. I will give you equations similar to this. You know, you will see where the double bond is, you will see where the single bond is, you will see how many single bonds is, you will see how many carbon-carbon atoms will be broken for each, and then plug it in this equation. Remember, broken minus formed. We are breaking the bonds on the reactant side. We are forming the bonds on the product side to really fit in this equation, equation here. All right. So there's the bond formation for that. Let's see, lastly, the simplest of all, because of time factor, please complete that. Because of time factor, I don't want to, I hear the echo, mute everyone. I don't know if that helps. Anyway, the last part I want to look at in chapter 5 is the energy food we eat and in relation to energy. Energy is given off when we digest food, and the food value given on table 5.1 indicates how many kilojoules, all right, are given off. Let me exit and then see if it's gonna work. Let me see if that will help. Starting a new recording. Yeah, that helps. So, the food we consume.
Can I just ask a quick question before we move on?
Yes.
Would you mind just giving us the answer to that last learning check, just so that like whenever we work it out, we can just check ourselves?
This one, if you want us to solve that, we can real quick complete this so that you know. Let me just look for my calculator, make sure we indicate that. So if you have, these are the reagents, right? So 5 times 413 plus 3, what, 348.
Yeah,
right?
I just wanted to make sure that there was so much confusion and people need our hands easy. So
Plus 348, 358, 358, plus forward 463. So you should get for the reagents 3 times 495. So this is 47. You get these 47, 47 and 19 kilojoules. These are amount of energy required to break the bonds. Did you get that?
Yes, I did.
Lauren, yeah, that is what it is. So once we know the amount of energy proken, we now calculate for the form. This was from this equation. Look at this right here. We have carbon dioxide with 2 double bonds on either side. And from the balanced equation, there is a 2 in front here. So 2 bonds being broken times 2, that is the where 4 is coming from here. So you see where 4 is coming from, right? Because we are breaking 2 carbon, oxygen, there are 2 of them, times 2 from the coefficient in the balanced equation. That's where 4 is coming from. And then for H2O, if you look at the H2O here, let me just bring my whiteboard here. There is H bonded to oxygen, and then oxygen bonded to what? To another hydrogen for H2O. So we are breaking 2 HO times 3. That is where the 6 is coming from here. That is where I have my 6 here. So if I now add the 2, 4 times 799 plus 6 times 463. 463 is 559 74 kilojoules. You got this, right?
Yes.
And yeah, there are some numbers which I wanted to explain here where they're coming from. Now, from the equation here, the equation you need to understand, it is bond envelope is broken minus the sum for form. So here we will have to subtract, all right? We'll have to subtract from these 4719 minus 59 74. All right, what we get 47019 minus 5974 negative negative 1255 kilojoules, negative 1255 kilojoules is the amount of it's the enthalpy for the reaction. That means heat is given off for the negative. Did you get that, Lawrence?
I did.
Yes, and then you just have to know. The thing is, some folks might say product minus reagent, confusing with the enthalpy for standard enthalpy formation. We had product minus reagent, but here is reactant. That means the bond being broken in the reagents minus the summation of the energy required to form the bonds. Energy to form the bonds.
Right. Yeah. I just want to make sure that I had it right, just because this slide that we're on right now, whenever it said like add the bond energy and then subtract it for the ones that were broken, I just wanted to make sure that I was getting the sum that was right.
Yes, that's clear. You got it right. That's how I look at it. Being broken, we are breaking on the reagent. Being formed, it should be formed. Thank you. Yeah, I hope no more background noise, Alexandria. I had to exit my whiteboard and come back again. So moving forward to the, this is the easiest. The food we consume has caloric content in energy, and you'll be given these values. in the sense that each type of food, be it carbohydrate, fat, protein, apples, and whatever, the amount of heat given, I mean, the fuel value in kilojoules per gram, in kilojoules per gram or kilocalories per gram. If you look at the amount given here, all right, for every 1 gram of carbohydrate, burned, this is how much energy you will be released. The kilocalorie here, nutritionist used the uppercase CL, which has 1,000 lowercase calories. Wherever you see your energy content of the soft drink, it means here. So when you see kilocalorie here with the small calorie, you can relate to 1 uppercase calorie is the same as 1,000 calories. So for every 1 gram, all right, the food value here will be used to determine how much energy in total. What is the fuel value of a given amount of food? If you are given, you know, a meal consumed by an individual, with each gram, we can calculate the food energy or the fuel value. Let's say, for example, let me just give you an example on how these fuel values are used in calculating the total energy content. Suppose somebody consumed 5 grams of carbohydrate and 5 grams of protein. If we know 1 gram gives this, or this is the fuel value for 1 gram, we multiply by 5 the fuel value for carbohydrate. You look at the fuel value for fat, and then you multiply by 5. Remember, this is per gram. So the point is, if you know, or if given these values, the fuel value for each type of food, you can calculate the total fuel value for a meal based on what? Based on this fuel value. It's just a question of using dimensional analysis given these values. I'll give you the fuel value for each type of food, and given you the meal composition and say, what is the total fuel value for this? You'll just have to add for all of them. Now, if you look at the carbohydrate, fat, this literature file is given from the table. You'll be given for the table for this, get the fuel value for each one of them given that. I don't want to just go in details into other sources of energy. You can read that. See, we have about 15 minutes. We can start chapter 6, please. Complete by Sunday, just like I said earlier on, complete by Sunday, chapter 5 to be on the same page, chapter 5 homework assignment. Last week I checked, all right, I checked the chapter 4 and about 63 at that time were yet, about 63 folks were yet to start chapter 4 homework assignment. Please catch up with the homework assignment on that. Let's see, in chapter 5, all right, we looked at the energy associated with chemical reaction. Chapter 6, we will change the subject to shifting gears to looking at the atom now, which makes up the matter. It's the basic fundamental building block of matter. I will post, Lauren, I'll post chapter 5 homework momentarily. Keep an eye on the announcement and check your UNF email account. It should be following up shortly. Should be available shortly. Now, we are shifting gears in chapter 6 and looking at the atom now. We are zooming in to the atomic structure. What comes to your mind when we talk about the electronic structure is how the atoms or how the electrons are arranged in an atom. Now, in a dark room, there is no way you can know where things are unless you have what? Unless you have light. So at the outset, we will start by looking at the start by looking at the properties of light in order to really look at the atomic structure, going through the development of the models of an atom to where we are in terms of mechanical model, how they visualize the atom. But first, while we are looking at the nature of light, we need light to really understand what is going on at the atomic level, to see the electrons, to talk about the electrons. And light, all right, let's see if I can minimize this and have my PowerPoint slide. Will, hopefully it's gonna allow me, no. I wanted to, let's just go with the way it is. I wanted to say that light has, all right, light has two properties. Before we look at the electronic structure, we need to understand the what? The nature of light, that it is like a wave. We know what a wave is. And I'm going to just show you something you can tag with. The electromagnetic radiation. Let's see. This is a wave, right? And a wave is described, or properties of a wave. We have what we call the wavelength. Light has a wave property. That means it has what we call the wavelength here. We call this wave length. Distance between two adjacent peaks. Distance between two adjacent peaks is defined as the wavelength, or two adjacent troughs. All right, it could be two adjacent troughs. Right here, the lowest point is called the trough. It also represent the wavelength. So light, whether it is coming from the fluorescent lamp or the bulb in your home, it is coming in form of a wave. Light behave like a wave, it has a wavelength. It is part of electromagnetic radiation moving through a space with a known speed. Now, one thing I want to bring to your attention is, why do I have this notation on my whiteboard? So that you can reconcile with the colors of the rainbow, or the visible region of the visible region of electromagnetic radiation, something we can see with our naked eye. If the wavelength ranges from this dimension, 700 or 400 nanometers to 700 nanometers, we talk about the visible region of electromagnetic spectrum. The rest we cannot see. This is how the colors of light are arranged according to increase in the wavelength. R, O, these are arrangement of colors according to increase in the wavelength, and that is what is meant, or what this diagram means in terms of arrangement of colors of light we see based on the wavelength, the distance between two adjacent peaks. You should know what this stands for. This stands for red, all right? This stands for red. This stands for violet. This stands for indigo. This stands for blue. This stands for green. This stands for yellow. This stands for orange. Richard of York-Cross bananas in vain, depending on how you look at it. That is how you can tell, all right, which light has the longest wavelength based on the color you look at it. If it is red, it got longer wavelength based on what I just gave you. It is within the visible region, something you can look at. It is part of electromagnetic. You can look at that, or you can make a conclusion that indigo has a longer wavelength compared to violet, or yellow has a longer wavelength compared to blue, or orange has a longer wavelength compared to what? Green, for example, and vice versa. So I can say here is one shorter wavelength, high energy, all right? Whereas on this side, this one is longer wavelength, and here is low energy. Before we do that, there is a property for light we call what and we use this. This is new, which stand for or indicate frequency. Frequency of light. This is the number, or I can just write in full. This is simply number of complete waves passing a given point per what? Per second. It's represented by the word nu. Nu, it's not V. This is like that. It's just like V. It's frequency. And frequency is given per second. This is the units per second, or hertz. H for hertz. This is the unit for frequency, passing a given unit. So if you look at this diagram, we can say that this end on the visible region of electromagnetic radiation have high frequency. Let me use that. And then this will also have on this end low frequency. They will have low frequency. So these are the characteristic features you need to remember and tag, reconcile with the visible region of electromagnetic radiation. These will have low frequency compared to blue light. Just give you the nature of light when we talk about the nature of light. So the phi here is stand for frequency, nu, we call it nu, quick simple, and the number of complete waves passing a given point per second, frequency. The subscript here, this is the same as, you know, for math, when we say, or when we denote this, it means the same thing. Hertz or per seconds used for frequency. So if I look at these two waves, this one is more energetic compared to wave A. This one, you know, this has low frequency, this has high frequency. This has shorter wavelength, higher wavelength. You need to know that because there will be problems on conception looking at the energy without necessarily calculating and say that this one has flow. So I've covered the properties of light, that it has a wave. There is what we call the amplitude, or amplitude, I forget that, which represent the intensity. This is the amplitude. Right here is amplitude, and it will just indicate the intensity of light. Intensity of light. So I've just shown you that this is straightforward. Look at the PowerPoint slide here that the vertical height of a wave is called amplitude. Wavelength, distance between two adjacent peaks. Frequency, the number of waves passing a given area. We don't have anything to do with the area or median or median. That's what I want to point to you. And let's see now part of electromagnetic spectrum here. If you look at this electromagnetic radiation, this is what I was talking about, the visible region of electromagnetic radiation. The violet is down here, the red nanometers. Of course, it's more energetic. There is the X-ray. That's why whatever you could for or dental, they use X-ray. It's more energetic, it can travel through. The radio is microwave. What we'll be focusing is the visible region, and it lies between 400 nanometers and 700 nanometers. What I mean by this is the distance. It is the wavelength, and when we say wavelength now, you should know. If you look at the R, means wavelength is increasing as you go from left to right. One thing you need to remember is regardless of the frequency or the wavelength or electromagnetic radiation, they drive or they travel with the same speed. All electromagnetic radiation, whether violet, indigo, yellow, they do what? They travel at the same speed. We call this a speed of light, and it's 2 or literature value of 3.0 times 10 to positive 8. And it turns out that this equation, just gonna be the last thing I'll talk about, is the wavelength. We will start from here, the relationship between the wavelength of an electromagnetic radiation with its frequency is related using the speed of light. This is the speed of what? The speed of light. We will start from here next time. I want you to start reading chapter 6. We'll start from here next time. If there is no question, the class is dismissed. I think somebody may have asked a question. Let me see. Can you also post last lecture session? Alexandria, I tried, I started last time recording the lecture. Unfortunately, I ran out of the memory on my laptop. desktop and the MP4 file could not be saved. I reached out to the tech support at UNF. They couldn't help either, but I fixed it. If you have any question, please let me know and I'll be able to assist you. I'm sorry about that. I tried the best I could. I had to delete some files today. That's why I couldn't post last time, but for today, it should be there. The class is dismissed. There's no question. I will see you again, same time next week. Have a wonderful afternoon. Thank you.